It's my pleasure to be here today, speak on behalf of my collaborators named here who helped put together this slide deck. And there are some other collaborators who I'll mention as we go through this. So the background that really leads to the motivation, previous 3D modeling of the Uinta Basin shown in this figure reached a couple of findings. So in that figure, the black line shows the measured ozone, and then the colored lines are model results, and they're pretty different. There's a sensitivity to the emission inventory, which isn't surprising. But then there was also a comparison of two different chemistries that we use in the models. And that's the green and the blue lines, which are very different, which is an interesting finding that needs to be followed up on. The difficulty is, in order to make that comparison, you had to switch between two models. So there are two things going on there. There's a change in model and a change in chemistry. And so that's difficult to interpret. So the objective here is to get those two chemistries in the same model in ChemX and compare them and have much more certainty about that comparison and draw conclusions. That's our objective. So there are three tasks to get there. First one, add that mechanism, the RACM2 mechanism, the one we want to add, into the ChemX model. And so to do that, we had a collaborator, Professor William Stockwell. He's the developer of the RACM2 mechanism. And he worked with me to put that mechanism into ChemX. And because he did that work, he sort of finalized that version of the mechanism for us in September of 2021. We call it RACM2 S21, because it's very handy to keep track of specific versions of these mechanisms. So first thing, add the mechanism. Second, set the model up. That means make consistent sets of model inputs to run these two different chemistries, which that's painstaking work. And so the way that we did that is my team at Ramboll built tools, and Seth's team applied those tools to make the model inputs. And then the third thing is do the modeling and make the comparisons. And that's where we are at the moment. We just have some model results that I can show you today. They're very fresh. We think they're right, but just bear in mind they're very fresh results when I show them to you. So the team, the co-PIs are myself and Hui Tran and Seth's group. So my role is very much with a chemistry, and Hui's role is with preparing the emissions and applying the models. People who are helping is, as I mentioned, Professor Stockwell. He's with the University of Texas, El Paso, helping on this RACM2 chemical mechanism. With me at Ramboll, Tejas Shah helped with the tools for the emission processing. Chris Emery is very familiar with modeling the Uinta Basin, and so he helps with a general interpretation of what we're doing. And Seth is involved to, again, help with the interpretation and great knowledge of the measurements that have been made. So that's the team. Just to say a little bit about these chemical mechanisms. So, ozone forms from the chemical reactions of VOCs and NOx in sunlight. How many reactions are we talking about? How many VOCs? If you were to look in the atmosphere in the Uinta Basin, perhaps there are tens of VOCs that are there in significant amounts. But when they react, you can get thousands of reaction products. And each one of those reaction products can have multiple reactions. On the right, I'm showing some reactions for just one of those products, and it can go in all these different directions. And that's a simplification, by the way. That's not all of the possibilities. So you can have tens of thousands of different chemical reactions that are potentially happening, which is far more than we can put in a model. But fortunately, molecules that are structurally similar their chemistry tends to go in similar ways. There are patterns. And so we build these condensed mechanisms with many fewer reactions and species that try to capture those important patterns. So that's what we mean by a condensed chemical mechanism that we put in our models. So now with this work, Chemix has 3 different condensed mechanisms. They go by these acronyms. CB6 on the left, which we usually use, RACM2, the one we just added, and another one, SAPRAC, version 2007 on the right. And just under the figures, I listed how many reactions we have. So we're in the 200 to 500 reaction range. That's a number of reactions that we can deal with in the models. So what the figures are showing, and this was really a QA step for me to make sure we'd implemented the chemistry correctly. This is a Los Angeles summer condition, and we're showing how much ozone you can make with various amounts of VOC and NOx. So we call it an ozone response surface. And you get the most ozone, the highest point on the surface, when you have both VOC and NOx. Yes, we know that. And the shape of these surfaces is very similar. So definitely, these mechanisms are way more similar than they are different. You could look closely and you could find differences, but this is a Los Angeles summer condition, so I really don't want to dig into this because we want to look at the Uinta Basin in winter. So this was a QA step, and it looks good. So there's a lot of details here on the model configuration, which I think are important to keep in the slide deck, but perhaps to summarize, we're using a previously developed version of the Chemix model that has a 1.3 kilometer grid, so it has fine resolution. The emission inventories are very important. We're using UDAC's 2017 oil and gas inventory, and we have the detailed speciation, VOC speciation work that Seth's group has previously done. We've done the work that's necessary to get that into both chemical mechanisms. Then for the non-oil and gas sources, we're mainly using NEI 2014. We didn't include biogenics or windblown dust in this modeling, which I don't think that's really going to change any conclusions because we're modeling very cold, stagnant conditions, so that won't hurt us. Hui Tran did a lot of careful comparison of the emission results. So these are maps showing our emissions for various species. I apologize, they're hard to see, but these were QA steps. Perhaps focus on the conclusions. With the 2 mechanisms, the NOx emissions are identical, which they should be, so that's good. The spatial patterns agree, we're getting the stuff in the right place. If we look at alkenes, which are reactive VOCs, there is perhaps a 10% difference. I've thought more about this, and I think actually we're not quite including everything we should include in the RACM2 plot, so I think it's actually less than 10%. If we look at some of the other reactive VOCs, so aldehydes, aromatics, and ketones, I mean, we have differences of 1 or 2% between the 2 mechanisms, so this is very good agreement, I think, and it speaks well to the careful work that we did, and the spatial patterns agree. So I think we're very comfortable with the QA and the implementation of the emission inventories for the 2 mechanisms. Okay, if we look at the ozone results then, maybe first look at the figure on the bottom right, the little inset, which is showing ozone differences over our whole modeling domain. And we're only seeing differences in the Uinta Basin because they're very special conditions here in an ozone episode in the Uinta Basin. So the chemistry is making a difference in the Uinta Basin, but not elsewhere. The 2 figures at the top show the episode average hourly ozone with CB6 and RACM2. The RACM2 figure, you can see it's a little more yellow, so there's slightly more ozone, and that's borne out by the difference at the bottom. And it can be up to 29 ppb more ozone at one place in 1 hour. So, that is a difference. We look at time series at some of the monitoring sites. So again, the black is showing the measured. And then the green and the blue are these two different model runs. I have to move quickly. So with both chemical mechanisms, the model is still lower than what was measured, which perhaps speaks to there are still things to understand in the emission inventory and how we're modeling meteorology. So there are differences between the two mechanisms, but they by no means close the gap on their own with the observations. But there are, as we mentioned previously, there are differences there that are big enough to look into. And if we come back, previously we looked at maps for hourly ozone. If we look at MDA8 ozone, the 8-hour ozone that we're most concerned about, and we look on the 2 days, during the heart of the episode when concentrations were highest, the February the 5th and the 6th, RACM2 is producing more 8-hour ozone, and it can perhaps be as much as 17 ppb more in certain parts of the basin. So there is a difference here. So the summary then, this is where we're at. The RACM2 chemistry is implemented and it seems to be working for modeling these conditions. And it simulates more ozone than we get with the CB6 mechanism. And those enhancements are largest during the most stable conditions. What do we need to do next? We have some additional QA testing to do to make sure that that chemistry is working right with the aerosol chemistry in the model. And then we have a tool in the model called chemical process analysis that I think we can really start to now look at the interesting questions. Why are these two mechanisms different? I mean, I think we can't say more until we understand the reasons for the differences. And then we'll be wrapping up in June. Thank you.
Thanks so much. Who has questions?
So how are you dealing with the meteorology? So are you using WRF for the meteorology? And then I know that that area is notoriously difficult to simulate with a meteorological model. So are you doing anything to the snowpack, or was it not relevant for that February case?
Oh, the snowpack is enormously relevant. And yes, it's modeled with WRF, and WRF has snow cover in there. And I didn't do it. I wasn't involved in the WRF simulation. Okay. I think it would be fair to say it's getting a lot of things right, but there's always room for improvement.
Because there are some studies that have actually had to manually add in the snowpack to get that radiation budget correct. So
you can get the snow cover for WRF. There are satellite products that will give you that.
We have time for one more, Randy?
Yeah, your trends look really good on the models as far as when the peaks and spikes occur. Have you thought about trying to back calculate your emissions as far as if you need to increase the emissions by X amount, would they match your data? And I'm thinking that because I know there's been some discussion about particularly the tanks and whether those were underestimated in their emissions.
I think there are a lot of interesting questions that can be asked. I think these comparisons of chemistry models, we don't do that very often, hardly ever. We don't do it enough. So we're really focused on that question. I'm sure the answer interacts with the emission inventory, and we won't be able to look at all of the possible interactions, but perhaps we can get some answers on the uncertainty in the chemistry.
And we also have a comment from Hui in the chat that says we used WRF setup that included MODIS, I assume that's MODIS, snow albedo to improve the surface characteristic.
So that's a satellite recognition of where this snow is.
Okay, great. Thanks so much, Greg.